everyone. I'm Sophia, co-founder of Bagaut.dev. For those who are first time, welcome to the Bagaut community. We're very happy to have you here. And please join our Slack workspace. I just shared the link in the Zoom chat. Today, our guest is Azalia Mirhoseini. She's a staff research scientist and she's a tech lead of the machine learning for systems team. Throughout her career, Azalia received many awards, and among them, the best PhD thesis from Rice University, and Azalia's was also included in the list 35 under 35 by MIT Tech Review. Azalia, thank you very much for joining us today. We're very excited and very much looking forward to your talk.
Yeah, thanks, Sophia, for inviting me, and it's great to see these kind of events happening, and happy to contribute. So I'm going to talk about some of the work that we have been doing in Google Brain machine learning for systems and chip design team. And to start, I just want to motivate why we are interested in this domain. And the reason is that in the last decade, the success of machine learning has largely been due to the great systems and hardware that have been developed. And our motivation here is that it's time for to return the favor and use machine learning to transform the way systems and hardware are designed. We also have other motivations, like this paper that came out last year that shows if you want to follow the current trajectory of the amount of compute needed to achieve certain accuracy on ImageNet, if you want to achieve 1% top accuracy, we would need 10 to the power 14 more gigaflops or computation than what we have right now. Or this other famous chart by OpenAI that shows that this exponential growth in the amount of computational needs for successful AI runs. And this is happening, this exponential growth is like happening really fast in a span of a few months. So given that AI is so power hungry, we do need to develop better systems and accelerators that can serve AI, and so we can continue the current trend. Now, a lot of problems in systems and hardware design have a common format, and that is a combinatorial optimization on a graph structured data. Here I give you a few examples. For example, compiler optimization, chip placement, data center resource allocation. They're all problems that appear in systems and hardware, and the input to all of these are like a graph, a computational graph, where the objective is to do some sort of a resource allocation or scheduling on the nodes of this graph such that the runtime or the other performance metrics for this task is optimized. Now, we are interested in taking a learning-based approach to solve these problems. And the reason for that is the following. The traditional methods for these problems are always based on either heuristics, like branch and bound methods, or hill climbing methods such as simulated annealing or ILP solvers. But learning problem has this property that they can, as it appears from the name, they can learn the underlying implicit trade-offs that appear in an optimization problem and leverage those trade-offs in order to optimize certain targets that we have without us as human experts coming in and trying to find those implicit trade-offs. The other property is that the learning methods, they can gain experience as we solve more instances of the problem and become experts over time. This is not the case for pretty much any of the baselines, because each baseline is developed. A lot of thinking goes through creating like these ILP methods or other solvers, but none of these have this property that they can improve over time on their own and self-evolve. But learning-based methods have this property. And the third one is that we know very well how to scale and distribute platforms and train really like models with billions of parameters, such that they learn from complex context and information. Now, in the rest of this talk, I go through three of the problems that we have been working on in this domain. And the first one is device placement optimization. So device placement, first, let me define what the problem is. So the problem is how we take a large model and map it to the devices that we have, say GPUs or TPUs, such that the model runs as fast as possible, whether for inference or training. And of course, there is this trend towards larger and larger models. So this is becoming an important problem. So this was a project that we started more than 2 years ago at this point. This was our big intro, like beginning first project on ML for system design. And what we did here was to pose the problem as a deep reinforcement learning objective, where the policy, the deep RL agent, basically gets a neural network as input and gets a set of available devices and outputs assignments of the ops in this neural network onto these available devices. And once we do that, we can run one step or a few steps of this neural net, evaluate the runtime, whether it's for training or inference, we do the corresponding steps, just to measure the runtime per step, and then use that as a feedback to update the policy. So next time the policy proposes new partitionings of the model, and over time this gets optimized. And what made us really surprised in the beginning was the type of placement that the policy were coming up with. For example, this is the neural net I'm showing here. These are the ops of an LSTM, two-layer LSTM, two-layer encoder and two-layer decoder, plus the softmax and attention layer. And each of these different colors correspond to the GPU device that the op has been placed onto, and the white color is the CPU. So a lot of the ops next to each other are placed onto different GPUs, but we were getting better results in terms of like training time, given this partitioning of this language model, compared to the baseline, where at the time the state-of-the-art baseline before this work was to place every layer of this large LSTM onto a different GPU device. So we had 4 GPU device and a CPU. That was the placement. And what we realized that the policy, by just showing the runtime and asking the policy to optimize for the runtime of this neural net for this given placement, our policy was able to come up with like fairly balanced partition of the workload across the GPUs. Whereas the baseline one, even though it was highly balanced for the feed-forward part of the model, but when we looked into the full feed-forward and the backprop, like the full graph, it turns out that a lot of the workload has been placed, and that was hugely corresponding to a softmax layer, was placed onto one GPU, and that kind of could explain in part why we were getting better end-to-end runtime results. Here is another result on a vision model. Here is an Inception V3 neural net. Every branch here is a different convolution branch. And again, every color shows a different GPU. So the policy again put the embedding layer on the CPU, and then it did find some parallelism across the branches. For example, this 4 branches, each branch is placed on a different GPU. Again, all the learning here is done implicitly by just the only thing the policy has access to is trying out different placement, and we'll look into the runtime. And in this case, what we did was to place create a baseline, and that was the baseline that was used at the time was to place a copy of the GPU of this neural network on per GPU. So we did a data parallel replica, whereas in our case we were partitioning only one Inception V3 across 4 GPUs, but we ensured that both schemes have the same batch size. So essentially, we were doing the same computation. And what happened here is that in this case, we were not doing better in terms of GPU workload balancedness, because the baseline by default and by design was highly balanced. But the policy could come up with better runtimes and better placements because in this case, when we looked into amount of memory copies, the policy really optimized for memory copies across the GPUs, whereas in the baseline, there was a lot of like load, workload, and gradient exchange between the GPUs. So again, the policy implicitly learned this property. So when we started this project, we were focusing a lot on like training a policy from scratch every time to place a new device. And what we later, whereas our end goal was to generate a policy that generalizes across neural nets, meaning that quickly and at inference, we can quickly generate placements for any new neural net and map it to the devices. So basically, our goal was to create a policy pi theta such that it optimizes the reward function, which is, correlates with the timing across a data set of graphs of neural networks. And in this case, we focused a lot on graph representations because the policy needs to generalize across different graphs, different neural nets. So we use graph neural nets to embed the graph stage, to embed the TensorFlow input graphs. We use Transformer XL to really handle this large space of a large number of ops in the neural net. And basically, as the ops are coming into this model, they get embedded. And then the output of this policy is the placement of an op onto one of the available devices. And in this case, we got very exciting generalization results. For example, here, the black one is the method that we train a policy from scratch for just one target neural network. And then the red one, for example, here is when we take a pre-trained policy and just at zero shot at inference, we apply it to a new model. And the pink one is, for example, when we fine-tune. So we not only apply to a new model, but fine-tune for a few iterations on the new model. And as you can see, we got very reasonable results compared to the policy that trains from scratch. And keep in mind that the zero-shot model can generate these results in sub-seconds. So we can quickly learn to partition a new model onto available devices and achieve optimized runtimes. Here are some of the results. The benefit of this generalized policy was that we could come up with optimized models much faster. And also, not only that, in some cases, we even get better runtimes on some of these benchmarks compared to the model policy trained from scratch. If you're interested in these work, take a look at these some of these papers that I have listed here. The second project that I'm going to talk about along the same lines is learning to partition graphs. So graph partitioning is a classic problem in computer science. A lot of times when we do graph partitioning is because we have a very large graph, and our goal is to kind of break down the complexity of this large graph and work on smaller subsets of it. For example, this problem appears in VLSI design, in device placement, distributed social network clustering, and such. And a classic approach, again, for solving the graph partitioning problem is the normalized cuts objective. And here is, and to explain for those of you who are not familiar, the normalized cut objective takes a graph and partition it into smaller clusters such that the goal is that the volume of each cluster, meaning the number of nodes in the clusters, are roughly the same while we minimize the number of cuts across the clusters. So here is a mathematical formulation of what I just described. In this work, so we were interested to learn how to partition this graph, and we took a very simple approach, and that was take a node, develop a neural network that takes the nodes of the graph, and on the output side, it predicts the probability of assigning this node to each of the classes that are out there, or the number of clusters. Say if we have 10 clusters, the softmax size here has a dimension of 10, and the goal is how we, what is the probability of being assigned to each of these 10 classes. So having this, then we can write down or rewrite the normalized cuts objective as follows. For measuring the expected cuts or the number of cuts between coming out of the cluster, we can look into the probability of an edge existing in a cluster. For example, in this case, PCI is the probability of node I belonging to cluster C. So, and we can write this for all the nodes, and by multiplying the probability of an edge existing between two clusters, we can get the expected number of cuts between those two clusters. We can do the same for measuring the volume of a cluster by adding up the probability of all the nodes that belong to a cluster. Doing so allows us to write this expected cut, normalized cut objective, and now we can minimize this. We can use a gradient, stochastic gradient descent to minimize the loss associated with normalized cut. And as we are optimizing this loss, meaning as the loss is going to zero, the probabilities get shaped in a way that enables us to cluster the data. For example, here we have a cluster of cars and a cluster of birds that are that we want to, and we have this association graph, and we want to find these clusters. And this is, of course, a toy example, just to illustrate the technique. As the loss is going down, the probability, and as the normalized cut loss gets optimized, the probability of the cars belonging to cluster 1 becomes really high. The probability of these birds belonging to cluster 2 becomes really high. So then it becomes very, very easy. And we take the argmax here to cluster these nodes, and it becomes very easy to cluster them. We tried this technique on a large number of different data sets and different applications, from various device placement graphs to standard graph partitioning techniques, and we got a lot of exciting results over the strongest baselines. And the benefit of this method is that it scales to graphs with large number of nodes. We can easily do similar techniques as we use in deep learning. We can do batch optimization and place basically partition graphs with millions of nodes. And this method also has the ability to generalize to unseen graph data sets. And this method is open source, and the code is available on GitHub. And we have a couple publications on that as well. So if you're interested, please take a look. Now we want to go through the third project, and that is learning to optimize chip placement. So again, this chip placement is a combinatorial optimization problem that appears in chip design. And the problem is we have a graph. This graph describes the chip. The nodes of these graphs are standard cells or memories, and standard cells you can think of as logic gates like AND or XOR, and the memory and the macros are the memory nodes. And this graph can have millions to billions of nodes. The chip placement problem is the problem of placing the nodes of this graph onto a canvas such that we optimize certain objectives. For example, we minimize the total wire length of connectivity of the nodes in this graph. Imagine the edges are all there. We just want to place the nodes such that the total wire length of these edges is minimized. And then there are certain rules about, like, certain nodes cannot overlap, or if there is an overlap on certain other nodes, the density of the canvas cannot go more than a certain threshold. To just give you an idea of the complexity of this problem, I'm just showing that the search space or the state space for chip placement compared to chess and Go, which are two canonical games previously solved by DeepRL. And the space here is huge, enormous, like orders of magnitude larger than that of Go and chess. And there has been 5 decades of research, prior research on floor planning, on partitioning-based methods, stochastic methods, analytical solvers. And what we proposed here was a learning-based method. And this technique was purely based on deep reinforcement learning. And the way we train this deep RL agent was as follows. The agent starts from an empty canvas, and then it starts placing the nodes one at a time. In this case, we place the macro or memory nodes. And then once all the macros are placed, we use a force-directed method to place the standard cells. And the reason we do so is that placing standard cells is much better understood, and the standard cells are really tiny compared to the macros that have different shapes and very strict properties, whereas standard cells are very small nodes that needs to be placed. So once we place all the macros, we use force-directed methods to place the standard cells, and then we look into our reward function, which is an average of 3 different metrics, Y-length, congestion, and density. And then we use that to update the agent, so that agent next time, again, starts from an empty canvas and places the new ops. The optimization objective is train a policy pi theta that, given a set of canvases G and graphs, chip graphs, can optimize the reward, which is the weighted average of these metrics that correlate in the end with the chip's power, area, and timing. And I said in the beginning of this talk that these methods have the ability, learning method have the ability to learn and improve and evolve over time. So our motivation here was that we wanted to train an agent that, instead of like training from scratch every time it sees a new chip graph to place, it can we can train it on a large data set, so the policy learns how to place or do this decision-making task for a large number of chips, and then we use that pre-trained policy to quickly, with some fine-tuning, place a new netlist, which is the chip graph. To do so, we needed to do some changes to the policy, because when we started testing a policy that was trained on, say, chip 1, when we tested it right away on chip 2, we were not getting good results. And we did all sorts of techniques that we use in supervised learning, for example, for transfer learning, for example, freezing certain layers and retraining initial or end layers. But we weren't getting good results because, and then the policy, and that this is a challenge with the policy and deep RL policy, because now instead of predicting one label, the policy needs to predict a large number of actions, and that's where to place these nodes. So transferring that and learning from one graph to the other becomes much more complicated. So our intuition was that a policy that can transfer across chips, at the very least, should have a good grasp of seeing a new chip and seeing the placement, evaluating the reward, like the goodness of this placement. So if the policy can generalize on that, we thought maybe it can never generalize, not only generalize placing new chips, right? You should be able to first evaluate or have a sense of the goodness of a placement, and then be able to optimize for that metric. So we developed a training data set of 10,000 placements and their labels. And the labels here was the reward function, for example, congestion and Y-length. And we took it from 5 different chip blocks and generated a diverse data set. So different placements associated with different violence and congestions. And the placements were generalized as we were training some initial RL models. So we had high quality placement and low quality placements on the same graph. And then we spent a lot of time on first devising a supervised model that can deliver good results on predicting these reward functions on test data set, so on unseen chip graphs. And for doing so, we needed to innovate on the architecture of this graph convolution network, because a lot of the focus here was on the edge and while length of the model. So we had to focus a lot on edge embedding and creating meaningful representations of the edges of the convolution. So once we had this supervised supervised model that could predict violence and congestion, we took this model architecture that we found here and we used it as the encoder part of our deep RL policy. So now our deep RL policy on the encoder side had this new convolutional architecture and new kind of embedding that could generalize across chip netlists. And and on the decoder side, we used a series of deconvolution layers as well as some masks to kind of account for different rules that are out there in terms of placing the nodes, the chip nodes on the canvas. So once we had that, we actually did see generalization results. For example, in this GIF, you can see on the left side, we have a policy that we are training from scratch on a new chip graph. Here is a CPU RISC-V netlist. On the right side, we are using a pre-trained policy and apply just fine-tuning step to place this RISC-V chip. And on the right side, we could quickly come up with meaningful ways and optimized ways to place the chip, whereas on the left side, it took a while for the placements to become optimized. Here is another result that shows the effect of this policy that transfers across graphs. Here we can achieve cost from a pre-trained model more than 30 hours faster than what we achieve for a policy that we train from scratch for a targeted chip netlist. Here is another data that made us very excited, showing that the policies actually become better after we train them on larger data sets. Here, the yellow policy is the one that's trained on the largest data set we had, and it's 20 different chip blocks. And the medium one is trained on 5 blocks, and the green one, the small data set, on 2 blocks. And as you can see here, that the placement cost, even at 0 shot, we are achieving much better results applying these policies on unseen chip graphs if the policy is trained from larger and larger data sets. And of course, if you fine-tune these smaller data sets for a long time, they might get to the point or close to what the larger policy gets to. But our hope is that we can make this larger data set, as we collect more and more data set, we can make the policy such that even at 0 shot, it can generate high quality placements. Here is a blurred version of a TPU block that we actually developed and placed. And the method, at the time, it took 24 hours, but right now our methods run between 6 to 12 hours, whereas the baseline placement took several weeks, and it involved human experts in the loop, and we got like the same results, maybe roughly slightly better. But the automation and making this process much faster is what was the significant impact of this work. Here are some comparisons that we did across various TPU blocks with very advanced technology node sizes, and we also compared with academic baselines and the manual baselines, which are designed by the expert team, and we got comparable or better results than manual, and got much better results than the academic baselines that were out there. And this work generated a lot of attention from various outlets, but that we think it's just the beginning, and there is a whole lot of work that needs to be done and can be done with machine learning to improve the way we design systems and chips. To summarize, in this talk, I talked about the impact and the importance of learning for optimization problems, that they can find implicit trade-offs, they can gain experience and self-evolve, and they can scale readily to complex problems. And I talked about 3 problem areas that we focus on, namely device placement, graph partitioning, and chip placement. Here are some papers and of the topics. Some of them I discussed in this talk, and some others are in general the papers from our group on the topic of machine learning for combinatorial optimization and system optimization. And with that, I can conclude my talk.
Awesome. Thank you. I see there was a huge discussion in the chat. Guys, if you have questions, maybe you can unmute yourself and ask directly, Azalia. Nerit, you had a question when Azalia just started her talk about like a certain slide.
Actually, it's okay. But the thing I'm curious about, Azalia, is I missed this in your talk. I think I was like talking in the chat, but how do you, so when you're like evaluating chip placements, right? If you're doing it with reinforcement learnings, how do you handle rollouts? Are you doing this with simulations? Like, how does that work?
Yeah, we have proxy cost, proxy while length, and congestion and density. So we use that, but in the end, once we have placed it, we report results by running an EDA tool to give QOR results. So our optimizations are done with the proxy cost, and then we feed that into an EDA tool to get other results, for example, DRC and other area, TNS, WNS, and such.
Thank you.
I see Mihai Toder ask question. Mihai, do you want to ask your question?
He said he can't talk right now. So.
Oh, okay.
Maybe I can read it from text.
Oh, so yeah. He was wondering what force-directed algorithm was being used.
Obviously, a very simple force-directed method, like when we started it, we used the original 1991, I believe, paper on force-directed method. Recently, we have modified that and used DreamPlace, which is a state-of-the-art standard cell placer, which is an analytic solver based on deep learning that we are using for that.
Okay. From Kathleen, a question regarding comparisons with existing discrete optimization techniques, like simulated annealing.
Yeah, we have put those results, some of those results in the paper, and we have done extensive internal comparisons with simulated annealing. The benefit of simulated annealing is that it's very easy to implement, and but we were not able to get good results from that, especially as the chip become more and more complex. Some observations that I can share with you, and in terms of how deep RL is better than simulated annealing, and we hope that we can publish a paper on that, is its sample efficiency. So deep RL, we could show that it's roughly 2 orders of magnitude more sample efficient than simulated annealing in terms of the number of samples we need to get to the same accuracy. The other benefit of deep RL was that it could better optimize for non-smooth cost functions such as congestion and density compared to simulated annealing. In terms of while length, both methods are very good at optimizing that. And the third property was that with deep learning, because we embed the nodes of the graph, the model kind of learned to put like the macros in the same data path closer to each other. So because the embeddings of those nodes were more similar, that is not something that a black box method such as simulated annealing can observe. And that definitely helped us.
Question from Anand. Have you looked at the other areas of chip design like timing, power analysis?
You mean using, yes, actually. So for example, there are existing projects on using machine learning for design verifications, for predicting DRC or power outputs of a certain design. Yeah, we have a lot of ongoing projects in those areas.
Guys, do you have questions? Actually, I have a question. So as I understood at OpenAI, their approach is, increase computation, and that probably will lead to AGI. I'm just curious to get your perspective. Do you think like the increase of computation can solve like significant problem in machine learning?
Yeah, I definitely think that it definitely is an essential need that we keep and increase the rate of designing more powerful computational accelerators to ensure that we achieve the kind of results we want to see AI and we are all excited about. So yeah, I think we can solve many problems. I'm not sure if I can say all of the problems in AI, but many problems would not be a problem anymore if we had like infinite compute or significantly more compute that we are now. And that's kind of like why in our team, we are super excited about this line of work because we think this is the enabler of AI and the future of AI.
Awesome. Okay. Someone can't unmute themselves. Just a second. I will try to unmute you.
Oh, sorry. I could unmute myself. I just wanted to say that I can just ask my question first instead of writing it in the chat. So I just have a quick follow-up regarding like, what do you feel the future of using deep learning methods, so to say, for so not necessarily RL, for other discrete optimization problems, traveling salesman, scheduling problems, stuff like that, which are still in the domain of classical. I don't think the existing methods are competitive on that domain yet. There's been some work with pointer networks and so on a while back, I think, around convex halves and TSPs and stuff like that. But what do you think the state of the art for other problems is right now? And what do you think the future development might be?
I'm definitely very excited about deep learning and deep RL and deep learning in general for discrete optimization. And that's why we spend a lot of our time and our focus on this. I totally agree that there is a lot of work to be done to kind of like beat the state-of-the-art analytical solvers. It took us some time in the chip placement problem to be able to do that, like beating even like simulated annealing or ILP. It took us a lot of like domain knowledge on the deep RL side to really making this agent like learn and improve things and kind of surpass the existing baselines. But what I'm excited about these methods is that as we make progress, a lot of the things that, for example, I feel like I learned and our team learned from the placement problem can be applied to other deep learning optimization for other discrete problems, regardless of what that problem is and how it's different from the specific chip placement problem. And especially the power of these methods. And I think that's key on how these methods are going to replace the state-of-the-art or existing baseline is that these methods can learn from context and from the environment. So I don't have a lot of hope for these methods beating black box baselines. Rather, I feel like these methods shine whenever we feed in data and context that these baseline black box solvers cannot leverage, but the deep learning methods can learn and can find those implicit like trade-offs and rules that they can come up with to use them to optimize the targets. To give you an example, in all of these works, whenever we kind of open this optimization space, like by inputting like detailed embeddings of the graph, of the canvas, of all the constraints, that's where these methods start working and becoming really powerful.
Actually, I missed a question, one follow-up question from Anand. Is the chip placement solution generalizable across different design and technologies?
Yeah, we have been using it across a large number, a large number of designs within a TPU chip. As far as I can tell publicly, there are a lot of like different types of block within a TPU chip, from like the compute versus like the IO and memory and other blocks. So we have tried on a lot of blocks within a TPU. We have tried it on other sort of like edge device, and like I showed here, RISC-V. And we have tried it on advanced technology nodes, like really advanced technologies sizes. So in that sense, it has worked across different functionalities and technology node sizes.
I see Dashan raised hand. Dashan, do you want to ask a question?
Yeah, hi Sally. We virtually met about a year ago. I have two questions. One is, what's your defense against the EDA experts? Because whenever I talk to them, they said that all these papers are nonsense. And they still said that to me last week. Very reputable professors. The second is, it's very interesting for this transfer of prior knowledge. So you mentioned you have like 10,000 placements to learn from. But 10,000 for training sounds very small. How far do you foresee if we add a few zeros to that, and how much the transfer can really achieve? That's my two questions.
Okay, so one question was like regarding the data set, and I missed the second, like in terms of these papers. So just to give you an idea, like the methods that we have developed has been used in the latest generation of TPUs, and we have a TPU team that in that round of designs, they did all the work to design the placements for the blocks, and we had a very strict criteria for picking the designs that our method picks compared to the human expert baseline. And still on the majority of designs, on the majority of the blocks we were given, on the vast majority.
So my question is in the paper you have you still take like 6 hours to train, and just following up on the previous question from this OpenAI stuff, asymptotic limit of large models and large data. Suppose we augment your 10,000 pre-training example and make that 1 million or 10 million. How much of the 6 hours can really be reduced? I know this is extrapolation, but do you have any idea?
Yeah, I mean, like what I was saying, continuing what I was saying, that we still like, so the method was used in the design of our results were used over the expert designs in the design of latest generation of TPU that was actually taped out because the results were better. But we were getting these results in like 6 to 12 hours, whereas the baseline some of them did take several weeks, right? Several weeks took to. So now the question is how much we want to reduce, like making the 6 hours like 1 hour or half an hour doesn't change. It's very exciting for the users, right? The users would love to see that, the physical design users to do that. So in that sense, and I definitely think having a larger data set by doing augmentation can help a lot, just like I was showing in this graph here. So we had 20 blocks. As we had 20 blocks, our zero shot, meaning the sub-second placement, was way better than using 2 blocks. When I talked about that 10,000 placement, we were using 5 blocks, but different placements of them. So definitely we can reduce this time. But what is more exciting is the quality. Like if we can push the quality of the zero shot better, so we can use this as a quick feedback for upper level optimizations before we get to the placement stage, right? So this is something that we're very excited about.
I see a question from Dave. What is the number of inputs to the neural network when you're partitioning a graph with 1 million nodes with the network?
So we use a batch size. So we use a fixed batch, for example, 256 nodes as input. And then we can use the distributed system. So different workers get a batch of 256, but we can have like 10,000 or so inputs at that time that goes into the network.
So I have a question from Robert. Can machine learning or reinforcement learning methods be applied to chip routing as well? What would be the benefit?
Yes, it definitely can. And the benefit would be that in this case, what we are solving here is the global placement problem. That's what I showed. And if we do routing, then we can fully optimize, and we have much more control to optimize for all the metrics, such as timing and everything. Because here, when we are solving the placement problem, we are having a rough idea where the routes are, and based on that, we optimize the placement. Whereas in full routing, we have to basically connect every 2 nodes together, every 2 standard cells and nodes together. Again, that's another example of a combinatorial optimization decision-making task. Right now, simulator annealing, other heuristics are being used as baseline, which deep learning can definitely help. But there are a lot of areas in chip design that deep learning can help. So it's like important how we prioritize what problem can use our help most at the moment.
How do you make that decision of prioritization?
So for us, working with, for example, in this project, we work in the chip placement project, we work very closely with the TPU team, the team that builds Google TPUs. So looking at their schedule, just talking to them, it was very clear where their where the shortcoming is and where the what the bottlenecks are. However, like in the overall system, if you don't have access to that, there are a lot of like areas of interest currently in research. For example, doing design space optimizations across the chip design space from architecture all the way to place and route is a really exciting topic, a very important topic. One way to prioritize tasks is that, for example, what can help this this design space optimization? What can enable that? Because right now there are all these manual, heuristic, and really time-consuming steps in chip design that kind of doesn't allow us to do design space explorations and really globally optimized accelerators.
Can you share like what other research projects your team is going to tackle in the future?
our team, what kind of future. I think I kind of like pointed to that. So something that we are very excited about is kind of getting quick feedback, like enabling quick feedback all the way from architecture design to place and route. So currently, just to motivate this this problem, currently there is like 2 to 2.5 year period for designing a new big accelerator, such as the new TPU or probably the same for GPUs, right? The reason for that is there is like this huge sequential process with a lot of like manual efforts in between, where across different stages of chip design, there are different experts designing and operating on different works, and then they pass the candidates to the next level of this stream pipeline, and then to the next level, and all the way to, until the chip is sent to manufacturing. What we are very excited about is to automate parts of this flow that also enables the architectures at a very high level, a very good understanding of how their design and designs at this high level will result into very end of this pipeline chip performances. Because currently there could be like a few like multiple times mismatch between what the evaluators tell us at the architecture level compared to what we get at the very end before the chip is manufactured. And removing this mismatch and kind of enabling faster feedback for the architecture level design is what makes us exciting. Makes us very excited. And to relate that to machine learning, that would be how we do sample efficient design space exploration. When we are searching over a large space, designing new, basically, like creating new designs from all these actions that we are available. How can we do this in a very sample efficient way? Because every time we have a new design, if we want to evaluate it, that evaluation can take a long time. So how can we, with less evaluations, come up with designs that kind of are optimized in terms of our objective functions?
Thank you, Azalia. I see some follow-up question from Dave. Dave, you can unmute yourself and ask a question. Hold on, I'll unmute Dave. Okay, something doesn't work. Okay, so basically his follow-up question is this. If 256 nodes go into one neural network and the total distributed system can input 10K nodes, does that mean that there are 40K neural networks across the distributed system? He posed this question in the chat, so you can read Azalia if you want.
Yeah, so oh no, there are no we do this in a batch. So all the batches, so let's say we have 256 per neural network, and then we have 10 or 16 of these neural networks. That means we have 16 devices, say 16 TPU workers, and then in the next round we pass in the next set of batches. So we don't process the 1 million at the same time. But what we do is that we calculate the portion of the cost function associated with this, say 16 times 256 nodes, and then keep that, cache it, and then send the next set of nodes. Yeah, the number of neural nets we have is like 16 or so.
Mm-hmm. So I saw Kevin Go raised hand. Do you want to ask a question?
Hi, can you hear me?
Yeah.
Okay. Thanks for just sharing. And we have seen the paper of chip design with reinforcement learning, and it's awesome. But we have a question about the reinforcement learning network architecture of value-net design. And we know that the partitioning is trying to output the probability of the macro placement on the chip canvas. But what is the purpose of the value-net? Is it trying to evaluate the performance of the overall macro placement, or is there any other purpose of the value-net of this architecture? Thanks.
So we use value-net to basically, as part of our RL optimization, we have been using proximal policy optimization, or PPO, as our deep RL optimizer. And in that, we use value-net just to stabilize the training. We found that having a value-net makes the approach more robust. Basically, the curves that shows the return become much more robust if we have the value-net. Basically, the reason is that when we are calculating the advantage function, this value-net basically learns from existing historical data and makes our policy more robust and less noisy. So that was just like a common way we do optimization when you use DeepRL, just for robustness of the results.
So the output of the value-net should be a probability distribution, or other
no, it's just
discrete...
a number. No, it's just a number. Yeah, it's basically the discounted reward function over the episode.
Okay, thanks.
Yeah.
Okay, so there's one more follow-up question from Dave. Azalia, do you see it? How can you partition a graph with 1 million nodes by doing 16/256 nodes at a time?
So it's basically, you can think of this 1 million nodes. It's just like 1 million data examples in ImageNet, right? Just like we can process in one epoch, we go through these 1 million images. In this case, we are going through 1 million nodes. Each node is considered an example, basically.
Awesome. Do we have other questions? Yeah, I don't see any questions. Thank you, Azalia. Thank you very much. Such a great talk.